Ever find yourself kind of drowning in your own digital stuff? Like you've got photos, articles you bookmarked, maybe even voice memos, all this great stuff. But how do you really connect the dots between them? Beyond just searching for a specific word or the date you saved something. How do you get at those deeper links, the meaning behind it all?
You hit the nail on the head there. It's this disconnect between how we as humans understand the context and meaning of information and how computers traditionally store and organize it, often in these very rigid keyword-driven ways. It's a gap we often call the semantic gap.
Totally. Like I might have a photo of this amazing sunset I took and I tagged it orange, but what if I wanted to find other images that have that same warm, vibrant feeling, maybe some autumn leaves or even a painting with a similar color palette? It's tough to get those kinds of results from a simple keyword search.
You're exactly right. Traditional methods just don't cut it when you're trying to capture those more nuanced connections.
Hmm.
And that's where the whole idea of vector databases comes in. It's a way to represent your data, not as those rigid fields and keywords, but as mathematical representations called vector embeddings.
Okay, hold on a second. Vector embeddings. You're going to have to break that down for me. I'm picturing like a spreadsheet with a bunch of numbers, but how does that represent, say, a photograph?
I hear you. It sounds a bit abstract at first, but the basic idea is this. Imagine each piece of information in your collection, whether it's an image, an article, or an audio recording, is translated into a series of numbers, a vector. And here's the cool part. If two items are similar in meaning, even if they use different words or visuals, their corresponding vectors will be close to each other in this mathematical vector space.
So, like two articles that talk about the same event from different perspectives, their vectors would be clustered together because they share that underlying meaning, even if they use different language.
Yeah. Exactly. It's all about capturing the essence, the semantic core, rather than getting hung up on specific words or pixels. And this opens up a whole new way of searching. Instead of keyword matching, we can now perform similarity searches, finding items that are conceptually close to each other in this vector space.
This is blowing my mind a little bit. So, I could potentially dump all my digital stuff, images, text, audio into one of these vector databases and then find connections between them based on what they mean, not just how I labored them.
You got it. It's about unifying all those different types of data under this common representation, these vector embeddings, and then using math to find the hidden links between them, links that go way beyond simple keywords or tags. It's pretty powerful stuff.
Okay, I'm hooked. Let's dive into a specific example. Say I have a picture of a beautiful sunset over a mountain range. How would a traditional database handle that?
All right, let's walk through it. In a traditional relational database, that image would probably be stored as a chunk of binary data, along with some basic metadata like the file format, the date it was taken, maybe even GPS coordinates if your camera captured that. And then you might have manually added tags like sunset, mountains, and orange.
Right, those basic labels to help you find it later. But as we were saying, those tags wouldn't really help me find other images with a similar vibe, like a photo of a desert landscape with those same warm colors, or another mountain vista, even if it wasn't a sunset.
Exactly. Those more nuanced aspects, the overall feeling or mood of an image, those are things that traditional tags just can't capture. And you'd be hard-pressed to find those kinds of connections using a keyword-based search. This is that semantic gap rearing its head again.
Okay, so tags aren't the answer for these deeper searches. Tell me more about how these vector embeddings actually work. How do they manage to capture those more subtle aspects of meaning?
It all comes down to numbers. A vector embedding is essentially an array, a list of numbers, where each number represents some aspect of the data's meaning. It's like a numerical fingerprint that captures the essence of the image, the text, or the audio.
So if two items have similar vectors, it means they share a lot of those underlying characteristics, even if they look or sound different on the surface.
You got it. Think of it like this. The closer those vectors are in this multidimensional space, the more semantically similar the items are. So if you have two pictures, one of a mountain range and another of a desert landscape, both bathed in the warm hues of sunset, their vectors might be pretty close together because they share that warmth and vastness, even though the specific content is different.
You mentioned earlier a simple example with a mountain sunset having a vector like 0.91, 0.15, and 0.83. Can you break that down further? What might those specific numbers mean in relation to the image?
Sure. In that simplified three-dimensional vector, each number represents a high-level feature of the image. So that 0.91 could correspond to the degree of elevation change high for a mountain range. The 0.15 might indicate a low presence of urban elements, meaning it's a more natural pristine scene, and the 0.83 could represent the intensity of warm colors, which would be high for a sunset.
So if I had a picture of a sunset on the beach, the third number, representing those warm colors, would probably still be high. But the first number for elevation change would be much lower.
Exactly, you're catching on quickly. The vectors would reflect those key differences and similarities. Now, remember, real-world vector embeddings are much more complex than this simple three-dimensional example. They often have hundreds or even thousands of dimensions, making them much more nuanced and capable of capturing those finer points of meaning.
Okay, I can imagine that makes things pretty complex. But the core idea remains the same. Similar vectors mean similar meanings, right?
Absolutely. The beauty of vector embeddings is that they allow us to represent and compare information in a way that aligns with how we, as humans, understand meaning. It's about moving beyond the literal to the conceptual.
All right, so how do we actually create these vector embeddings in the first place? Where do those magical numbers come from?
That's the job of what we call embedding models. These are sophisticated machine learning models that are trained on massive data sets of images, text, audio, you name it. They learn to extract the key features and patterns that represent the meaning of that data.
So there are different embedding models for different types of data, like one for images, one for text, and so on.
You got it. Each model is specialized to understand the nuances of its specific data type. For example, CLIP is a popular model for creating vector embeddings for images. GLOVE is commonly used for text, and Wave2Vec is often used for audio.
It's like having different translators for different languages, but in this case, they're translating data into this universal language of vectors.
Yeah, that's a great analogy. And the way these models work is pretty fascinating. You feed the data, whether it's an image, a text document, or an audio clip, through the model, and it passes through multiple layers, each extracting more and more complex features.
So for an image, the first layer might identify basic things like edges and shapes, and then as it goes deeper, it starts to recognize objects, scenes, and eventually the overall mood or feeling of the image.
Exactly. For text, it might start with individual words and then learn to understand the relationships between those words, the context, the sentiment, and so on. And by the time the data reaches the final layers of the model, it's been distilled into this high-dimensional vector that captures its essential meaning.
It's like squeezing out all the juice and leaving behind this concentrated essence in the form of a vector. Pretty cool stuff.
It is. And it's those vectors that we then store in the vector database, ready to be searched and compared.
Okay, so we've got our data neatly organized as vectors. How do we actually use this for searching? This is where the similarity search comes in, right?
Precisely. Let's say you want to find images in your collection that are similar to a new photo you just took. First, you'd convert that new photo into its vector embedding using the appropriate model. Then, you'd use a similarity search algorithm to find the vectors in your database that are closest to that query vector.
And the closer the vectors, the more similar the images are in terms of their meaning and content.
Exactly. There are different ways to measure this closeness or similarity between vectors, but the basic idea is that vectors that are close together in this multi-dimensional space represent items that are conceptually similar.
So instead of searching for specific keywords, I'm essentially searching for a certain feeling, a certain vibe, a certain concept. That's pretty powerful.
It is. It opens up a whole new way of exploring and connecting with your data. You could find articles that share similar ideas, even if they use different terminology. You could find songs with similar moods, even if they're in different genres. The possibilities are endless.
Now, what happens when your collection starts to grow really large? Comparing a new vector to every single vector in the database would probably take forever.
You're absolutely right. That's where vector indexing comes in to save the day. It's a set of techniques that help speed up the search process without sacrificing too much accuracy.
So it's like creating a more efficient filing system for these vectors so you don't have to search through every single one.
Exactly. One common approach is to use approximate nearest neighbor algorithms, or ANN algorithms for short. These algorithms are designed to quickly find vectors that are very likely to be among the closest matches, even if they might not find the absolute closest one every single time.
So it's a trade-off between speed and absolute accuracy, but in most cases, the speed gains are well worth that slight compromise.
Absolutely. Think of it like this. If you're looking for a recipe for chocolate chip cookies, would you rather sift through every single recipe book in the library, or would you rather be pointed to the section on desserts and cookies?
Definitely the latter. That makes perfect sense. Can you give me some examples of how these ANN algorithms work?
Sure. One popular algorithm, it's called HNSW, which stands for Hierarchical Navigable Small World. It essentially creates a multi-layered network where similar vectors are linked together. So when you search, the algorithm can quickly navigate this network to find the closest matches without having to look at every single vector.
It's like having a map that shows you the shortcuts through this vast vector space. What about other algorithms?
Another common approach is called IVF, which stands for inverted file index. It's like dividing the vector space into neighborhoods or clusters, grouping similar vectors together. So when you search, the algorithm only has to look in the most relevant clusters, drastically reducing the search space.
So both of these techniques are ways to avoid brute force searching through every single vector, making the whole process much faster and more efficient.
Precisely. And these are just a couple of examples. There's a whole world of fascinating algorithms out there that are constantly being developed and improved.
Now, you mentioned earlier an application called Retrieval Augmented Generation, or ARG. Can you tell me more about how that works and how it might be relevant to someone managing their own personal knowledge base?
Absolutely. RAG is a powerful technique that combines the capabilities of vector databases with the generative power of large language models. Imagine you have a collection of documents, articles, notes, all this valuable information you've accumulated over time. With RAG, you could break these down into smaller chunks, convert each chunk into a vector embedding, and store them in a vector database.
So it's like creating a personalized knowledge base where all your information is semantically organized as vectors.
Exactly. Now, when you have a question or you're trying to recall something specific, you could phrase your query as natural language. That query would be converted into a vector, and the system would use similarity search to find the most relevant chunks of information from your own collection.
It's like having a super smart research assistant that can sift through all your notes and find the most pertinent information based on the meaning of your question.
That's a great way to put it. And then those retrieved chunks can be used to answer your question directly, generate new ideas, or simply provide context and background information. It's a way to make all your knowledge more accessible and interconnected.
That's amazing. It's like having a personal AI that can help you make sense of all the information you've gathered over time.
Exactly. And that's the power of vector databases and techniques like RA. They allow us to move beyond simple keyword matching and start interacting with information in a way that's more aligned with how we think and learn.
This has been an incredibly insightful deep dive. I feel like I have a whole new perspective on how we can manage and connect with our own information. Vector databases really are a game changer. They allow us to go beyond surface level connections and start uncovering the hidden relationships and meanings that lie beneath.
I completely agree. It's about moving from data to knowledge, from isolated bits of information to a cohesive understanding of the world around us.
It makes you wonder, what other possibilities are out there? What new ways of interacting with information will emerge as this technology continues to evolve? It's a really exciting time to be exploring the frontiers of data and knowledge.
It is, and I think we're just scratching the surface of what's possible. As vector databases and related technologies mature, we can expect to see even more innovative and transformative applications emerge, changing the way we learn, work, and interact with the world around us. It's a journey worth following, for sure.